I went into, looked through the windows into Louis's office one time around 1965, and he was reading this strange book. And I asked him what he was doing. He said he was learning Fortran, which he did. Which he actually wrote I think he wrote a program to calculate pi, and not surprisingly lost interest very soon. I was going to talk a little bit about bubble chambers, which I know not a lot about, but I think that the interesting thing, as Art had said, was that Louis had the vision to decide that to do this, to work in this area of particle physics, you needed lots of statistics, and so he started on this program with Art and Lynn and Frank and Frank Solmitz they built this series of bubble chambers. One interesting thing is that the 15-inch is just a stubby version of the 72-inch. It has all the same properties, including a very unique reflection system inside we called coat hangers, which was a way to work with only one window. So you could illuminate from one side and take pictures from the same side and not get a flare. So that was a very clever and a breakthrough for those two chambers. And the 72-inch chamber was, of course, long, so you could get pictures because the interactions really took place over several feet. And Art talked about the choice of hydrogen. I think Louis characterized other materials used by other people as strawberry jam. The real I think genius that Louis had was to realize that all the action takes place on the interface of different technologies. In this case, big accelerators, cryogenics, of which this was probably one of the larger tanks full of liquid hydrogen ever made, and digital computers, which were just coming to be important at that point. So I think, to me, that was a lesson of Louis, which was, if you want to do something worthwhile and do work on the edge, you have to work with the intersection of many pieces of technology. And I think, to me, that was the great lesson. Of course, the bubble chamber, which I'll remark very shortly, was 400 or 500 liters of liquid hydrogen. It had this very large magnet that was fairly homogeneous, and it had a tough engineering problem, which was it had to work at around 60 or 70 psi, and it pulsed every 6 seconds with about a 10 psi pulse, which is a frightening thing to an engineer because of potential fatigue problems and working at very low temperatures, and you had to interface this enormous piece of optical glass, probably the biggest made, to this aluminum tank. And they invented some very fancy gasketing material, actually used indium, because it's soft at low temperatures at the 20K where it was working. So I think the other statistic which is interesting about the bubble chamber, which is at its maximum running, which is probably a 50% duty cycle at one pulse every 6 seconds, it produced something like 800 miles of film in a year, all of which had to be scanned and measured. So now I have to push this somehow to move a slide. I'm going to try. Up arrow. Up arrow? Down arrow. Down arrow. Okay, so thanks, Rich. So this is the same picture Art showed. It's the game was to show this to scan these pictures, and I'll talk mostly about the 72-inch chamber. A series of devices, of scanning tables were developed which allowed you to show one or 2 or 3 views at the same time and overlap them so you could tell if the particles were going up or down in the chamber. And a number of people were trained to identify various particles. This is an associated production experiment. Associated production makes a pi, hits a p, and gets a k and a lambda. The important thing, I'm not loud enough? Loud enough? Thank you. The important thing here is that you have to measure, first identify the picture and record it so later it can be measured on a precise measuring machine. So a number of scanners were brought in, many of them students. 2 of the most successful scanners in terms of being able to identify really good events here were Bonnie Thompson, who I think is here, and Janet Lannis, who later became Bonnie Glaser and Janet Alvarez. Hi, Bonnie. So a number of machines were developed to measure the coordinates of these images on film in all 3 views, and of course Art talked about reconstructing them. So let's go to the next slide. I'm going to come back to that one. This is what was called the MP1, which was a scanning stage that scanned 35 millimeter film from the 15-inch chamber. And what this person had was a keyboard, and also it had 2 handles which would move the picture back and forth, and they would measure the points on those tracks and measure the vertices. And that would go into, I think in this case, punch cards, which later got fed into a computer, either into a IBM 650 or later on into an IBM 709 and magnetic tape. So this was the first of the series of machines. The next one was one to handle 72-inch film, which was a much fancier machine, which was called the Frankenstein. It was developed by engineers, by Jack Frank. I think Gene Banal's here. He worked on this with Jack. I think called Frankenstein because, of course, Jack Frank, and it's a monster, and it's also fairly ugly, I think. This one had one more characteristic, which was you could drive along the track. So it had servos so that you could follow the track, and if you wanted to, if you started back there, you could just drive. No, it's okay. You could just drive along a track and punch the coordinates as you went at some appropriate rate, so that you got 10 or 20 marks along that track. X and Y coordinates, and again, do it in each view. The next device, so this was the real workhorse for years on the 72-inch chamber. And it produced a lot of film that went on to magnetic tape and then on from there into the big computers. I don't need it. I'm not going to use it. Thank you, everybody. So basically using joysticks and operating handles connected to a servo stage. The accuracy of this machine and all these machines had to be something like 2 microns in the film plane, which is a fairly tough problem, particularly when you're moving this stage back and forth at high speed. The next instrument that was built, again, to try to boost the rates was the scanning measuring projector, which Bill Humphrey and Louis developed, which was to permit people to measure, to scan and measure at the same time. And this went online and actually produced, was also a real workhorse of the system. If you look at as time goes on here, here's where the MP1s, that first instrument I showed you, came on, and then they stopped, because that was the end of the 15-inch film. The MP2s, of which there were several, ran and kept running for some time. The SMPs, the scanning measuring projectors, which were the last one I showed you, came on here and ran until 67. And another device which was seriously problematic for some time was called the spiral reader, which had a different technique. What it did was go to a vertex with the XY stage and then scan in a spiral with a radial slit going out from that point. That meant that you could scan automatically a vertex, and you'd go to this vertex and do the same thing. You'd measure the coordinate of the vertex, then scan out in a spiral. If you remember, if you take these are all roughly circles because they're charged particles in a magnetic field. If you plot those in polar coordinates, they're straight lines of different slopes. And that's the trick you use to identify the tracks later in a computer program. So the spiral reader was a red herring around Louis's neck for some time. And here is a picture of it. It was about to be defunded and junked because it had a mean time to failure of about an hour. It would never work. It was just an awful machine. It was so complicated that it just wouldn't work. And so Frank Solmitz and I inherited it, and what we did was we proposed something which was fairly controversial at the time, but it turned out to be the right thing to do, which was we said throw out all the electronics and replace it all with a digital computer. And here's a DEC PDP-4, which was then connected and replaced all the electronics, and it made it work very well and made it very flexible and work very fast because you could automatically find the next frame and move things around. Fine. And so it became a very big producer of events. In fact, we worked very hard to make its production high because we actually had a little alarm on the seat to measure if people were actually sitting in the seat. The rule was that if you couldn't get up from the seat unless you had someone else to sit in it. And on top of that, the motion of the stage was done with a trackball, I guess the precursor of a mouse, which was on an air bearing, and we actually heated the gas for the air bearing so that the operator's fingers wouldn't get cold. So it turned out to be a successful instrument. It has another component which is not described here, but it had because these pictures were digitized, these straight lines were digitized, the tracks were digitized, they had to go into a computer program to recognize which ones were noise and which ones were really tracks and which ones were, and so we wrote a very large computer program, and Jim Burkhardt, who's here, wrote the program, and it operated, and at the peak load, it was running about one shift on the new CDC 6600 to recognize the tracks. So the whole thing actually worked as a system. Back to the output, one could ask, why not go higher than 1 million pictures a year? The answer is you can't. At one pulse of the Bevatron every 6 seconds in a 50% duty cycle, and an event per picture efficiency of maybe 1 out of 3, that's 1 million. You can't do more than that. So that was really the end of the statistics. So I think this is a picture of vision, that we had to measure lots of events, and that and the execution of a lot of complicated instruments which ended up going right up to the limit of what you actually could produce at LBL. So thank you very much. I want to say one more. Can I say one more thing? A second. Look, I really think that Art is too modest about his software. He didn't talk a lot about it. It is an enormously difficult problem to deal with reconstructing these tracks in 3 dimensions. The stereo angle isn't very big. There are if you can think about reconstructing the optical paths, they have to go through air, big piece of glass, and then liquid hydrogen. And they have to all match up. And then you have to correct for what really isn't a homogeneous magnetic field. It's really actually kind of not a great magnetic field. And all that had to be done. So it was a very big problem, and I think it was amazing that it got executed so well.